Хорошо. Тогда мы опять начнем по-русски, а потом перейдем на английский. Вообще глобально наш план на сегодня это поговорить про торические морфизмы, что бывает. Вот. Значит, что мы, наверное, сначала сделаем? Давайте мы сначала сделаем афинную часть, а потом я скажу, что такое торический морфизм. Вот. Есть две важных вещи. Вещь первая. Пускай у нас есть конус сигма-1 и решетка какая-то n1 и конус сигма-2 в решетке n2. И у нас есть гомоморфизм фи из n1 в n2. Просто гомоморфизм аддитивных групп. Что тогда? Тогда, ну все помнят, да, что тор у нас, по сути, как бы тор, в первом случае это n1 тензор DC без нуля, и t2 это был n2 тензор на c без нуля. То есть у нас, если задан гомоморфизм n1 в n2, то есть гомоморфизм тор. И утверждается вот этот фи из тора первого продолжается до гомоморфизма торических многообразий. У нас есть как бы у сигма первое, оно построено в решетке n1 при помощи как бы сигма-1. Берем двойственную n1, берем сигма-1 с галкой, пересекаем, берем спектр, все такое. Соответственно, и вот эта вот штука, она содержится у сигма-2. Тогда фи продолжается до гомоморфизма из u сигма-1 в u сигма-2. Тогда и только тогда, когда фи от сигма-1 сидит сигма-2. Да, давайте корректно написать фи. Ну вот сейчас. Давайте мы напишем, что вот здесь вот еще фи q. Оно будет быть из n1 над q, n1 в n2 над q. На соответствующих пространствах будет действовать. И вот мы хотим, чтобы фи q переводила сигма-1 в сигма-2. Понятно, что я имею в виду? Или какую-то картиночку надо? Картиночку надо? Хорошо. Окей, тогда давайте доказывать. Ну, еще раз, если продолжать данный гомоморфизм, то эта штука выполняется. Ну, как бы, в одну сторону очевидно. Вот в эту сторону будет очевидно. Потому что если мы знаем вот это вот вложение, тогда что мы знаем? У нас будет в обратную сторону, у нас есть, как бы, что нас интересует, сигма-1 с галкой пересечь с m1, и у нас есть сигма-2 с галкой пересечь с m2, правильно? Фи у нас идет в эту сторону, значит, есть двойственное отображение в эту сторону, которое там берет, вычисляет. И понятно, что вот это вот фи, я рисую звездочку, это в смысле линейное пространство двойственное, оно на самом деле вот из этих соображений будет переводить все те мономы, которые положительны на сигма-2, они будут переходить в мономы, которые положительны на сигма-1, потому что, как мы будем считать сигма-1, мы сначала отобразим как бы сигма-2, потом применим то линейное отображение. Так как мы попали внутрь сигма-2, то будет положительное значение. Понятно? Или не очень? Еще раз, вот у нас есть как бы фи бьет из пространства n1 над q в n2 над q. На них есть, то есть m1 это линейное отображение из этого в q, а m2 это по сути линейное отображение из этого в q. Как у нас действует... sorry, I finished this proof and then I switched to English. Еще раз, как у нас действует двойственное линейное отображение? Как мы линейное отображение на m2 переводим в линейное отображение на m1? Мы берем вектор отсюда, отображаем его туда и вычисляем то линейное отображение, которое у нас уже есть. Соответственно, сигма-2 склад означает, что наше линейное отображение на сигма-2 должно быть положительным. А теперь мы строим такую штуку. Вопрос, будет ли она положительна на сигма-1? Ну, ответ да, потому что мы же вычисляем ее на сигма-1, как мы применяем к ней стрелочку сюда, попадаем в сигма-2 и вычисляем нашу линейную функцию. Она положительная. Поэтому то, что мы получили новое, оно будет положительно на сигма-1. Поэтому мы попали в сигма-1 склад. This is the statement that suppose that we have a map of lattices and it induces the map of Toric. I want it to be extendable to a map from one affine Toric variety to another one. I say that it can be extended. It can be extended if and only if this is true. So one direction is obvious. So if this is true, then this is more or less obvious. And more interesting is the other direction. So suppose that we have a map of affine Toric varieties here. Let us try to show that the image of sigma 1 lies entirely in sigma 2. How can we prove this? On the contrary, suppose that it is not true. So we have some psi which extends phi from u sigma 1 to u sigma 2. So it is given on the torus, and we only need to extend it to all the other torus orbits. And if phi from sigma 1 is not in sigma 2, then there exists some element, some u from sigma 1 such that phi u does not belong to sigma 2. We have our separation lemma. Separation lemma says that then, by the separation lemma, so if we have some cone, this is our sigma 2, and this is our point. We say that there is some hyperplane which cuts one from the other. Hyperplane is given by an equation by some m. There exists some m. It is from the dual of this space. There exists m such that it is positive. It is positive on sigma 2 and negative on our phi of u. m is positive in sigma 2 means that m is in sigma 2 check, and m applied to our vector is negative. Okay? I assume that this is not strict and this is strict. One inequality is strict and one is not strict. Okay, let us continue. I think I continue here. What if we have a map of varieties here? If we have a map of varieties, there is the map on the regular functions. The map on the regular functions will map. I want to map. Yeah, so chi m, I chose chi m here. It is my good m. Chi m is a function on u sigma 2. And so it means that psi star applied to chi m is a regular function on u sigma 1. Okay? Then I know that any u from the lattice n is a one-parameter subgroup. So I have a t power u is a one-parameter subgroup of the torus. So it will give us a contradiction. What if I calculate chi m on this one-parameter subgroup? Pi star of chi m applied to tu. This can be calculated. So our map was a torus invariant, so it could be calculated at the, not in u sigma 1, but in u sigma 2. In fact, it will be equal to chi m from t power phi u. So it will be t scalar product m phi u. So this is negative. So if t tends to 0, this limit doesn't exist. So we are done. We have proved this statement in both directions. Okay. This is the first affine statement I wanted to prove before defining what is a toric morphism. So the second affine statement, the second is suppose that we have two lattices. So n prime, let be n prime in n a sublattice of finite index. Suppose that G is n quotiented by n prime, a finite group. And in this case, nq equals n prime q, and we take the same cone. Sigma is a cone in nq, which is the same as n prime q. Okay. As usually, it is a strongly convex rational polyhedral cone. Then, first of all, the first statement is about groups. So, G is isomorphic to homo from the quotient m prime over m to C star, which is in fact the kernel of the maps of Toric. So, as before, we have n prime which maps to n, which means that t n prime maps to tn. So this is the kernel of t n prime to t n. So in this statement, there is no cone. This is only about lattices n prime and m prime. Then G, our finite group G, acts on the big algebra sigma check intersected with m prime with a ring of invariance the same sigma check intersected now with m. And the third is so we have an inclusion here, so we have a Toric morphism for the Toric morphism. I didn't define what is a Toric morphism. Okay. We have a morphism from U sigma n prime to U sigma n. It is invariant. It is constant on G orbits. G acts on U sigma n prime. It is constant on G orbits, and so the quotient is isomorphic to U sigma n. So should I explain something? If you are not familiar with the algebra of invariance or with quotients, I can give some detail. Or maybe I can give some very basic example, maybe even in dimension 1. Very basic. Suppose that n is z, okay? And then prime will be, let it be 2z. What is our group G? What is our group G? Do you see? What is the quotient of this and these lattices? The two-element group, which has +1 and -1. Okay. So what is one torus and what is the second torus? So this one, t and prime, can be described as t square, where we take t from. This is the notation which agrees with the map. So, and when this one is mapped to this one, I mean, this is the inclusion. So, if we take t square and map it here, then +1 and -1, they both map to 1. So the kernel is our two-element group. And what about the ring of invariance? If we act on Cx by G, where -1 x maps to -x. What is the ring of invariance? Which are the polynomials which are invariant under this action? The polynomials C, X, G in this case, these are polynomials which depend on x squared. So they contain only the even power of x. If it has some odd power of x, we replace x by -x, and this polynomial changes. So the ring of invariance is exactly this one, which agrees with our statement. Sigma check intersected with the bigger lattice is exactly all the even numbers. And what about the morphism? So the toric varieties are C1 in both cases. So this is the two-sheet cover. We take the map x squared, and C covers C twice. Okay. This was the example, and now I want to prove this statement. If you... Да.
Действует на торическом выражении, которое мы построили, или на вот...
Да.
На решении?
Хороший вопрос. Yeah. So, what is the action of a group? What is the regular action of a group on an algebraic variety? So we say that, so X is an algebraic variety, and we want G acts on X. It means that we are interested only with the regular actions. It means that it acts polynomially on X. So for each pair Gx, there is so it is a regular map from G times X to X, and automatically, if G acts on X, G acts on the regular functions on this variety. Okay? So
мы как бы взяли какое-то действие на торе и представили, ну, ложные характеры записали как...
Сейчас, смотрите. Вот такой момент. Вы в алгебраической геометрии, если не встречали, вы продумаете. Действовать на многообразии и действовать на регулярных функциях. Это, по сути, одно и то же. Ну, у нас у Affine пока что, вот в афинном случае, если вы действуете на x, у него есть координаты. Значит, на координатах вы действуете, значит, на всех функциях вы действуете. Вот, наоборот, если вы действуете на всех функциях, среди них есть координаты, вы их куда-то отобразили, О, прекрасно, у вас уже есть действия на x, каких-то координатах записаны. Вот. Дальше, что у нас есть здесь? Я еще не сказала, давайте я быстро скажу. Вот в каком-то месте, в том месте, где мы написали, что g это ядро отображения, у нас g сидит в торе tn'. Уже g автоматом за бесплатно является подгруппой tn'. А tn', она действует на вот этой штуковине. Ну, то есть раз tn' действует, то и g действует. А дальше, если g действует как бы на многообразии, то и на регулярных функциях есть действие. Как-то вот так вот. Ну, примерчики надо посмотреть, тогда станет легче. Maybe I should mention here that if it is written by some g here, on the regular functions, it is better to apply g minus 1. We will use it right now. Okay, so this was about group actions, and I think now we will try to prove this statement. Okay? So, for the first part, which was only about lattices. So we know that Tn is the homomorphism to C star from Z from M to C star. And we know the exact sequence M to M prime to M prime of M to 0. So is it clear? So we had the same for N, and now these are dual spaces. Okay, we can apply home to C star to this exact sequence. So since C star is divisible, the result will be also an exact sequence. 1 maps to maybe I read. Yeah, it is a contravariant, so home Z from this quotient to C star. Then it maps to T and prime. Then to Tn and to 1. Okay? Recall that we have a pairing. We have a pairing MQ. MQ maps to Q. If we quotient everything over Q. So we want to define a map by the following formula. So this finite group times this finite group to C star, it will act in the following way. So the class of element n prime and the class of element u will be mapped to the root of unity exponent of 2 pi I and the scalar product of m prime u. So it is well defined, because if we change m prime, if we add some element from m, then it will pair with u by an integer, and it will not affect. And in the same way, if we replace u by some element of n prime, in the formula, m prime and prime will be an integer, and it will not affect at the result. And we are done. We get that, in fact, we have the bijection between n quotient by n prime is isomorphic to homomorphisms from n prime and to C star. So if you do not believe in this proof, I can give another proof which is maybe another explanation which is seen by hand. Вы видите вот эту лекцию или не очень? Ручками через нормальную форму Смита хотите?
Ну, хотелось бы.
Давай. So, the second explanation of the same fact using the normal Smith form. If it is too abstract for you. Another explanation. As it is proved in the Varieties of algebra course, you have two lattices. You have two lattices n and n prime, and you can find the basis. So basis E1, etc., En for n, and some D1, E1, Dn, En for n prime. Так, вы это проходили? Еще раз, если есть две решетки, одна в другой конечного индекса, то можно выбрать способные базисы. Нормальная форма Смита и все вот эти вот мучения. Вот, окей.
What is this D1?
These are some multiples. I mean, it is the normal Smith form. If you have a lattice and a sublattice, so for a sublattice, it is well defined a rank. What is a rank? You can find the number of generators. Their number will be equal to the rank of the initial lattice. So you will have an integer square matrix with a non-zero determinant. If its determinant is 1, the lattices will coincide. N and n prime will coincide. If the determinant is greater than 1, so it is an integer. If its absolute value is greater than 1, you perform the integer Gauss procedure by the rows and the columns. So classically, D1 will be the greatest common divisor of all the elements of your matrix. Then D2, then D1, D2 will be the greatest common divisor of the 2 by 2 minus of your matrix. So if you impose the condition that D1 is the divisor of D2, D2 is the divisor of D3, etc., then this number of factors is uniquely defined. So it is the canonical representation of a sublattice in a lattice. So now what are the bases for M? We have some bases F1, the dual basis F1, etc., Fm for M. So is it clear what is the dual basis for M prime? Ananya, do you see what is the basis for M prime?
No, I think there will be no M and both will be N, right?
Sorry?
You have written the basis E1 up to En, and then you are saying the dual basis will be F1 up to Fm.
Yes, this is just a notation. I denote the vectors dual to these ones by Fi.
But I think both will be N, right? Because we are just going to take the functionals. So it will be...
These are the functionals which take the first coordinate, the second coordinate, etc. Ah, you mean N. You mean N is here. Yes. But what is the basis for M prime? This will be F1 divided by D1, Fn n divided by dn. These are the same linear functionals. I mean, if you take all the integers, this will be n and this will be n prime. This is the n and n prime. Then when we pass to the dual ones, if we draw m and m prime, this will be m, and m prime will be this one. Okay? And the quotient will be the same. So here we quotient n by n prime, we obtain z d1 plus z d2 plus etc. plus z dn. And here we quotient this by this, and we obtain the same z d1 plus z d2 plus etc. plus z dn. And what is our statement? Comma z from this quotient to c star. How is it constructed? For each z di, we should map its generated root of unity of c star of di's root of unity. Okay?
What is d? This side.
Any one of these ones, yes. So home from z d1 z z d2 z plus etc. to c star, to the multiplicative group. So since it is finite, we can map only to the roots of unity. Then any generator should be mapped to, so we know that d1 power of this will be 1. So this generator is mapped to the d1 root of unity of c. So any such homomorphism is a collection of roots of unity. But at the same time, the multiplicative notation n quotiented by n prime is the same group of roots of unity. Okay? Yes. For this group, this is the additive notation. You sum up the residues modulo di. But in the multiplicative notation, if you want this group to be described as a subgroup of C star, it is just you map this to the roots of unity of C star, some di's root of unity. And this is factorial because if you sum up two homomorphisms, it exactly means that you multiply the corresponding elements of group. So this is factorial. This is not only given coordinates. And this is clearly a bijection. We have two groups of the same cardinality, and it is injected, so is the bijection. Okay. This was about part 1. Now, what about the ring of invariance? What about the ring of invariance? So, we said already that G, since it can be viewed as a subgroup of P and prime, it acts on our variety U sigma M prime. So on the functions, so if G is applied to F, the action on the functions is given by F G minus 1x. If we consider the action which agrees with the action of the variety. So now what if we take some character and some point. So we want to investigate the invariance C sigma check with M prime, which are G invariant. Okay, so usually first people check the ring on invariance, and then they look at the quotient over the section. Which functions will be invariant? So all the functions are given by monomials, and let us check which monomials are invariant. We take some take M prime, we take chi M prime, and suppose that a point X is given by a semigroup homomorphism gamma, as we've done before. Then so among values of gamma, we have some coordinates, for example. And if when we apply G chi M prime, it will be first let me write. If we apply G to a point, if we apply G applied to gamma, it will map M to G M gamma M. It is how G acts on a point. And if we apply G to chi M, we will write G minus 1 M and chi M. So or any M from sigma check and intersected with M prime. So if it is clear that a character is invariant if and only if this is our element of the torus which acts on M. We saw in the previous slide that if it doesn't act on our monomial, then the monomial is in M. Okay. So if we take any non-zero element here, then there is a map which acts non-trivially on this element. Okay? For each non-trivial element here, so this is a good pairing, and we can choose yes, use such that it will give the corresponding map. So if in this statement, if M is invariant under the G action, but it doesn't belong to the sublattice M, we will find an element G such that this will be non-trivial, and so this character will change under the G action. This will be that it is not in the ring of invariance. And on the other hand, if it is in M, then clearly it is invariant under the G action.
Как эта формула вот M же, M на гамма-тем устроена? Гамма-тем это уже число.
Сейчас, это был полугрупповой гомоморфизм. Сейчас, вот
G-тем точка.
G от M это как бы число, которое у нас было, были единицы, которые вылезет.
Это...
Да, то есть по факту G это элемент Тора T4.
Все.
Причем мы знаем, что на M оно действует никак. То есть это какое-то число, это был полугрупповой гомоморфизм, который нам задавал точку, а это, соответственно, действие на функциях, и у нас вылезло G-1. Вот. Ну, как бы они нам не особо мешают, потому что если инвариантно, то вот эта штука всегда единичка тождественна. Окей. So,
M в квадратных скобках это...
это класс M. Ну, потому что мы берем, сейчас скажу, у нас было M', это большая решетка, правильно же? В двойственном теперь M' больше. Утверждается, что, ну, как бы G...
Фактор по M,
Да, да. M, нам важно с точностью до элемента вот отсюда. Потому что по-любому уже на элементах отсюда действует, ну, единичку дает. Ну вот. Ну, в смысле, G это гомоморфизм у нас из M' по M в C со звездой. Вот. В этом смысле, как бы, мы применяем класс элемента M. Вот. And now about the quotients, maybe I should say a few words. So, if a group acts G acts on X, and if we want to study the set of orbits, and if we want to give some structure, for some groups G it is nice, for some groups G it is not very nice. For example, the very classical example, C star acts on C2, it is a bad example. Bad. So xy maps to tx t minus 1y. Okay? What are the orbits of this action? So these are the orbits. Then 0 is the orbit. Then the line without the 0 and the other line without 0 is an orbit. And if you want to consider the whole bunch of orbits, there is no good topology on it. Okay? So this action is bad in the sense that if you take this set of orbits, you cannot introduce a good topology on it. Okay? But this group is infinite. This is C star. Now, if we take G finite, it is known that for any affine X, Cx G is finitely generated. So the ring of invariance is finitely generated.
X can be any variety.
Sorry?
X is any algebraic variety.
For me, any affine algebraic variety, because I write Cx. I don't want work with the rings at this point. Just any affine variety. And for finite groups, it is known so that so it can be included into Cx, which means that there is a map in the other direction, Cx quotiented by a finite group. It is mapped to some spectrum of this algebra, which will be, again, an affine algebraic variety. So the quotients of finite groups are well defined. So the fibers are the orbits, and everything is very nice, and everything works well.
Мы, получается, просто пропустили этот контекст, ну, по сути, то есть у нас написано, мы берем
да, вот сейчас
функции регулярных по какой-то решетке, потом от него спект, ну, коротко написано.
Я написала, да, ту вещь, которую я прямо сейчас не хочу обсуждать, которая скорее относится как бы к алгебре теории инварианта. Еще раз, такая вещь. Если у вас есть действие конечной группы, то кольцо инварианта будет конечно порождено. То есть это какие-то многочлены, сидящие в магазинах C от X. Вот. Поскольку эта алгебра будет конечно порождена, у нее есть спект. То есть есть некая афинное алгебраическое многообразие, просто алгебра функция будет такая, как здесь. Дальше, что мы видим? Вот то, что мы прям видим, что любая функция, которая инвариантна относительно g, она же по-прежнему является функцией на x. Поэтому тут есть вложение. Когда есть вложение, у нас есть стрелка в обратную сторону. То есть из x в спект того, что получилось, есть какое-то отображение. И вот это будет как бы конечный морфизм, свои будут орбиты g. Вот. Про это можно подумать отдельно, пока мы как бы этим будем более-менее пользоваться. Ну, то есть, если у вас нигде не было теории инвариантов, просто лучше какой-нибудь кусочек из книжки по теории инвариантов перечитать в этом месте. И сразу все станет ясно. Okay, so for the third part of our statement, it is just everything is in this statement. If we have u sigma n and u sigma n prime. So its algebraic functions is c sigma with m prime, and here the algebra of regular functions is c sigma with m. So this is the ring of invariance. So we know that c sigma check hand, sigma check with m is G invariant functions here. So this is included into this one. No. So this is included into C. And so we have the map in the other direction. A spectrum, this maps to here, and this map is constant on G orbits. Because constant on G orbits means that in some coordinates you act on your coordinates, but all the functions are invariant, so they don't change. Okay, so we have proved the second fact from the affine algebraic setting. Is it more or less clear? Готовы ли вы в это поверить сейчас? Ну вот, поразбираться с вот этим вот, как бы фактор по действию конечной группы. И давайте еще будут в семинаре примерчики, тоже должны полегчать. Okay. Now, the topic of today's lecture is Toric morphisms. So, Toric morphisms. First of all, what is a map of lattices? Phi is called compatible with fans. So, as before, phi is a homomorphism of groups M1 to M2. We have sigma 1 sigma 2, we say that phi is compatible with sigma 1 and sigma 2 if and only if for any cone from the first fan there exists a cone from the second fan such that phi sigma 1 is in sigma 2. Okay? It is better to say that phi q, to say that phi q is in this one, but it doesn't matter much. The example which we had before, do you remember the fan for the Hertzsprung surface? Do you remember we had a very nice fan? So this was our fan. We have two projections on, we can project it here on this coordinate line, and we can project it on this coordinate line. Which map is compatible with fans? So let us check. For this map, this cone goes to this cone. This cone goes to this cone. This cone goes to this cone. And this cone goes to this cone. Okay? And what if we project to the y axis? This is okay. This is mapped here. This is okay. It is also mapped here. But this is not okay. So its projection is the whole line, which is not included in the cone of the second fan. So this map is compatible with fans, and this map is not compatible. And so compatible maps are very, very important. I didn't define what is a toric morphism. A morphism between toric varieties x1 to x2 is toric if it maps the torus which is in the first one to the second torus and it is a group homomorphism. So phi restricted to T1 is a group homomorphism. Okay? Is the definition clear? And our statement, which I hope we will prove right now, is that as before, we have fans sigma 1 in N1 and sigma 2 a fan in N2 and first of all, in one direction, if we have phi from n1 to n2 be a map compatible with fans, then it induces a toric morphism. So you see that it is defined on n1 and n2, so it automatically gives us a homomorphism of toric. Okay? We say that n1 tensor with C star is our first torus, and n2 tensor by C star is our second torus. So if we sum up two elements here, we multiply the corresponding elements, and it gives us the torus homomorphism. So then there is, we want this map to be extendable to the whole variety. There is a map phi from x sigma 1 to x sigma 2 such that, so coinciding on T and 1 with phi tensor 1 from with this one. And on the other direction, if we have a toric morphism x sigma 1 to x sigma 2, so it is toric. Then it induces a linear map from n1 to n2, which is compatible with the fans. So it agrees, this theorem agrees with what we've had before. Okay, so our first example was about U sigma 1 maps to U sigma 2, only if the image of U of sigma 1 is in sigma 2. So that was the compatibility for a cone which contains only one maximal cone, for a fan which contains only one maximal cone. And the second was about the lattice refinement. So for the lattice refinement, in fact, we have the same cone or the same fan, but one lattice is a subset of the other lattice. So both these two affine cases were particular cases of toric morphisms. First of all, So the first part is easier. If we have a Z-linear map compatible with fans. I have to add one page. So we have done the most difficult part at the beginning of the lecture. So take a cone in the first lattice, in the first fan. We know that our map phi bar is compatible with the fans. So we know that there exists sigma 2 in the second fan such that it is mapped sigma map sigma phi map sigma 1 to sigma 2. So as we have done at the beginning of the lecture, the very first statement was, if this is true, then we have a Toric morphism. We've had a morphism. It will be phi sigma 1 from u sigma 1 and 1 to u sigma 2 and 2. So it is Toric because for 0 it is mapped to 0, and so it gives us a good morphism between tori. And now we have this, and also, if you know algebraic geometry, you can explain that the first variety is covered by charts. So in each chart you have a morphism. If you take an intersection of two charts, it will agree, because we have the same statement for any face of our code. And so it will give us indeed a morphism from x sigma 1 to x sigma 2. So it is covered by u sigma. So we go up and we obtain a morphism. More or less a definition of a morphism of algebraic varieties which are not necessarily affine should be given in charts. So it is done here. Okay, this was the easy part. Any questions? Верите вам это? По модели того, что морфизмы алгебрaickих многообразий задаются в каком-то афинном покрытии.
Ну, вроде верится.
Хорошо. Теперь в сложную сторону. Okay. So now we want to show that if we have a toric morphism, so it is it maps T1 to T2, and we want it to respect the fans. So we will need our statements from the orbit cone correspondence and about the closures. So the second part, phi induces a linear map from N1 to N2. Indeed, we can take, if we take some u from and 1, we have a one parameter subgroup lambda u from C star to P and 1. Then we can compose it with our map phi. Then phi restricted to P and 1. It is an element of K and 2. And so phi applied to lambda u is a one parameter subgroup of T and 2. So it is an element of N2. So it is a map which is Z linear, because if we sum up to U1 and U2, then we will multiply the elements of the torus. So it is an element. It is Z linear because we have the map from Tn1 to Tn2 is a group homomorphism. What next? Suppose that sigma 1 is some cone from the first fan. What do we know of? We have the T and 1 orbit of so we denote it by O1, O sigma 1. Okay? Our map is toric. So phi of this orbit is in sum another orbit O2 and orbit of T2. So we have the representative of this orbit. It maps to something in the second variety. When we apply the torus, since our map is toric, there is a commutative diagram. Either we can send it to the second variety and then apply that torus, or we can apply the first torus and then send it via phi. So any point of O1 belongs to its T2 orbit in the second variety. This is definitely not an equality, but it forms a part of this orbit O2. What next? What next? We know that O2 is O sigma 2 for some sigma 2 in our second fan. Okay? So our next step will be to show that this correspondence respects inclusions. So what is done right now? For each cone in the first fan, we found exactly one cone in the second fan, such that the orbit is mapped into this orbit. So only one sigma 2 for each sigma 1. Why does it respect the inclusions? Take tau 1 a phase of sigma 1. we also have O tau 1. This is O, this is not phi. This is O. This is the orbit of tau 1. And then it is mapped by phi. Suppose that it belongs to some O tau 2. We know that tau 1 is a phase of sigma 1, but we know nothing about tau 2 and sigma 2. Our local aim is to show that tau 2 will be a phase of sigma 2. We know that from the previous lecture, we know that O sigma 1 is in O tau 1 closure. The previous lecture, the orbit cone correspondence. We have discussed how to decompose this orbit closure into orbits. We know that phi is continuous and there's a risky topology. So, if we apply phi, we obtain phi O tau 1 closure will be in the closure of this one. O tau 2 closure. Okay, but this is decomposed into O sigma 2 such that sigma 2 have tau 2 as a phase. Okay? Мы смотрим, пускай О сигма 1, О тау 1 попадает в орбиту от тау 2. Мы эту орбиту обозначили тау 2. Проблема в том, что пока что мы не понимаем, как это тау 2 соотносится с сигма 2. Значит, чтобы понять, как она соотносится с тау 2 с сигма 2, замкнем. Вот у нас есть что? Известно, что О тау 1 переходит в О тау 2. Получаем, что О тау 1 с чертой переходит в О тау 2 с чертой. Здесь у нас лежит О сигма 1, а здесь у нас лежат только те орбиты, для которых сигма 2 содержит тау 2 как грань. Вот. То есть мы знаем, что у нас О сигма 1 здесь лежит, значит, та сигма 2, в которую оно перешло, содержит тау 2 как грань. Немножко плохо с обозначениями, но я надеюсь, что вы не запустите. Yes, at this step, I am showing that this tau 2 will be a phase of sigma 2. How can we deduce it? We know that phi is continuous, so in this inclusion, we can write the closures. If we take the phi of the closure, we will take the closure here. By the orbit cone correspondence, we know that this closure, how is it split into the orbits of the second torus?
Okay, it is actually union of all those cones which have tau 2 as a phase.
Yes. Some bad notation, I write bar here, okay? Is the union of O tau 2 bar which contain tau 2 as a phase. Okay? But we know that that O sigma 1 is in this closure. Again, by the orbit cone correspondence for the first variety. You agreed with this statement?
Yes.
Since we took a phase of sigma 1, then the orbit cone correspondence is in the first variety gives us this. So O sigma 1 is here. by phi, it is mapped, we know, to O sigma 2.
Okay.
But we know that it lives in this union of orbits. So O sigma 2 is one of these orbits.
Okay.
And sigma 2 contains tau 2 as a phase. So phi induces some theoretic map on cones, which agrees with the inclusion. And now, what next? It is not the end. It is not the end. By the beginning of our lecture, we obtained that phi applied to the affine set U sigma 1 is in U sigma 2. Okay? We said at the beginning of the lecture that if phi maps one curve to the second curve, then it can be extended to the affine Toric varieties. What was our aim? We wanted to show that what was our aim? We said that if we have a toric morphism, then it induces a Z linear map which is compatible with the fans. Okay. Sorry.
Наверное, мы из этого хотим сказать, что по тому утверждению часть сигма 1 внутри сигма 2.
Да, правильно. Правильно. Yeah, exactly. We said here that it is it respects the inclusions, and moreover, from the beginning of the lecture, phi of sigma 1 is in sigma 2. So why is it true? Because U sigma 1 and U sigma 2, they can be split into the orbits. Split by into orbits. So if O sigma 1 was the biggest orbit here, no, it was not the biggest, it was the distinguished orbit here, and all the other orbits which also are here, even the torus which corresponds to the 0 point, they map to the corresponding ones here. So we split this into orbits. For each one we have a phase of sigma 1, then it maps to some phases of sigma 2, and so they form part here. And by the beginning of the lecture, once we have this, we obtain this. And we get a map which is compatible with fans. So this linear map, which was in the lattices, is compatible with fans. Okay. We have proved the theorem. We will have many examples in the seminar. Maybe I want to give one example, which is a blow up. So what is a blow up? Combinatorially, it is if we split a fan. So the initial fan was this one. This is this is sigma prime and this is sigma. Okay? This is just we include here. It can be written any time when you have a fan and you split it. You add some rays and some colors in this way. Since we have a map of lattices compatible with fans, identity of the lattice and compatible with these two fans, we have a Toric morphism. So, if you remember, at the seminar we said that it is a subvariety in C2 times P1. In fact, we throw out the 0 point and we add P1 instead of it. And this map, it is a projection on C2. So, after today's lecture, we see that it is a torus map. Okay?
I think the arrow is going to be the reverse direction.
Sorry?
The fan arrow will be the reverse direction. No.
No. I mean, it is identity on the lattices.
Yes.
Okay? So, this cone is mapped to this part of this cone. And this one maps here. So our definition, phi respects the fans if phi sigma 1 is a part of some sigma 2. In this direction it is okay, in the other direction it is not okay. Okay. And maybe for those who know, we see that for in dimension 2, the toric varieties have only the quotient singularities. So each toric variety is covered by some affine charts, and each chart either it is already smooth, it means that the generators at the edge generate the lattice. Either it is smooth or it has some determinant greater than 0, but now we can take another lattice, subdivide n, and this cone will become smooth. And it will give us a map of some smooth toric variety into our variety, so that our variety will be the quotient of C2 by some finite group. Okay, I think I will stop here.
Can you just repeat the last statement?
Yes, the last statement. A toric variety.
I get that given a dimension 2 code, we can split it as much as time and we want, and then at last we will get a smooth code.
Yes.
Smooth variety. Code corresponding to a smooth variety.
I mean, we, if it is not the set of the generators of the lattice, we can subdivide our lattice in such a way that this cone will become smooth. And then we will have the same cone, but the other lattice, as at the beginning of our lecture. Okay? But now this variety will be isomorphic to C2. Each smooth cone in dimension 2 gives us a variety isomorphic to C2. So the new lattice quotient by the old lattice will be the group G. The quotient of lattices.
G will be a finite.
Yes, it is finite, and so C2 quotient by G will be isomorphic to our initial toric variety. Initial affine chart. Better, right? Initial affine chart. If I start with a non-necessarily affine variety.
How do you eliminate C cross C star?
Sorry?
C cross C star.
No, I mean, if I have an affine chart, why should I eliminate C? Okay, if it is a full dimension. If it is a full dimension, okay? Yes. Thank you for your attention. Any other questions? Okay, then the draft version of the seminar. I'm very sorry for. I'll finish it right now. Please don't put it to the chart. I will do it myself in some 10 or 20 minutes. Короче, задачу 3 я сейчас напишу. Она в проекте. Не надо вкладывать в чат, такой не будет смены. Ой, доброе утро. Хотите забрать? Как раз 6 для вас осталось.
What is question 7.2?
I wanted to take a problem from the book. I'm sorry. I will fix it right now. Так. Еще раз, я починю задачу 3 и скину этот чат. И листок 3 уже как бы здесь. Я надеюсь, что пока будет.
Листок 3.
В смысле 2.
Все.
Извините, заговорилась. Слушайте, вы не очень закроетесь, если у нас готовы будет не 5, а скоро 4. А что на трансляцию остановить, кстати?